diagram in high-DC cuprates. Professor Marino, please.
Okay, good morning, everybody. I would like to thank the organizers for inviting me. In particular, it's a great honor to deliver the opening session, for which I'm very grateful. I'm going to talk not about a new thing, rather it's a very old subject, but for which there are many issues that are not yet explained. So this is the summary of my talk. I'll go through different things, mechanism of doping, the model that we use. Okay. These are the collaborators. Reginaldo is a PhD student, Lizardo is a former postdoc, and Van is a professor at Federal University of Pará. The paper is in the archive, that's the code. So, as you know, high-TC cuprates were synthesized in 1986 by Bednorz and Miller. And after 30 years, there is a lot that's still not understood and properly explained. This is the basic structure. We have, in particular, these layers of copper oxide planes, which play a fundamental issue in cuprates. These are the copper oxide planes, which have copper, as you know, in this 3D9 configuration, and you have oxygens in these blue spots. For the parent compounds, the oxygen ions have 2 electrons per site, which implies it's a band insulator, whereas the copper lattice is a Mott-Hubbard insulator. This is another view of the copper oxide planes. I specify here the px and py oxygen orbitals, which are going to play an important role. So this again another view of the oxygen lattice. There are 2 sublattices with px and py orbitals, and these are the 4 vectors that connect nearest neighbors in the 2 sublattices. So this is the general schematic phase diagram. The main issues are these, of course, the superconducting dome, the anti-ferromagnetic dome, and pseudo gap. We are going to focus on basic features of this phase diagram, which so far have not been properly described by the available theories, even though it's more than 30 years from the... By the way, in conventional superconductors were discovered in 1911 by Camerlin-Ons, and BCS theory came in 57 approximately. But meanwhile, the whole quantum mechanics has to be invented in the meantime. So 30 years nowadays is quite a lot of time. So the first issue is the superconducting domes. This is the real thing. These are experimental data from these groups for 3 different compounds: LSCO, mercury, and bismuth. So there is no analytic expression for these domes. The most that we have is a parabolic fit, empirical fit for the LSO compound. That's the most we have. Now, another thing, if you take the multi-layered cuprates, there is a very striking phenomenological issue, that is Tc increases as we increase the number of copper oxide planes. Is a compound with 2, 3, 4, 5, but this increases up to 3, and after 3 it stabilizes and goes even a little bit down. So how to explain this? So this is just an example. For the bismuth family, we have the one-layered compound, the 2 layers, the 3 layers. So why these temperatures increase with the number of planes? There's no explanation so far. So this is another example with the mercury family. We start with the one-layer compound, the 2 layers, the 3 layers, and in the 4th layer it goes down a little bit and sort of stabilizes. So how to explain this? A third point that we're going to focus is again multi-layered compounds. As we increase the number of layers, the superconducting and antiferromagnetic domes come closer to each other and eventually superimpose. So how to understand this? How to explain this? So any theory of the high Tc cuprates should at least explain this phenomena. So what we're going to show here is we provide an explanation for these 3 issues. So this is again another view. This is the number of layers increases. You see that this superconducting dome comes closer to the antiferromagnetic dome and eventually superimpose. So let's start reviewing the mechanism of doping that you all know, but it's important to remember because it's crucial. As we dope, we introduce holes in the oxygen lattice. So this oxygen, which had 2 electrons per site, start to have some holes. And at the same time, you can show that magnetic textures, ischemia defects, are introduced in the copper lattice. So these are old ideas put forward by many people and explored in detail in these 3 papers that we wrote. So let's look at the oxygen lattice. Let's call Ne the number of electrons per side and NH the number of holes. Then we have that the number of electrons is 2 per side minus the number of holes. So the net charge per site is given by this expression here. And so we start with a completely filled band, and E equals to 2 and H 0. So this is 2. So as we start to dope the system, let's call X the stoichiometric doping parameter, and let's call X 0 this stoichiometric doping for which we have a half-filled oxygen lattice. And let's call NH X over X 0. So for X equal to X 0, we have 1 hole per site, which means 1 electron per site, which means half-filled. So for X equals to X 0, so X 0 is the stoichiometric doping for which the oxygen lattice becomes half-filled. So then we can write these expressions here. This is the density, so A is the area per site, which is given by this expression here. So x equals to 0 means a completely filled oxygen band, and x equal to x0 is a half-filled band. So the model we are going to use is given by this. So let's call psi dagger A and B the whole creation operator with spin sigma in sublattices A and B. Remember, A and B are the oxygen sublattices with px and py orbitals. So we have the first line is a hopping term. R sweeps the sites of one of the sublattices, and di are the vectors connecting to nearest neighbors. And then we have interaction term. Phi here is the Cooper pair creation operator. And we have this BCS-like interaction. If we integrate over phi, which is square and linear, we have a quartic interaction Lagrange. So the expectation value of this phi can be taken as a superconducting order parameter. The inspiration for this comes from this paper where we show that this kind of superconducting interaction is generated in the spin fermion type model. So again, this is the oxygen lattice, and let's remark that the horizontal links are different from the vertical links because there is a sign here. The vertical are always plus minus, whereas the horizontal are always plus plus or minus minus. So this gives an anisotropy, which is going to be responsible for the d wave character of this parameter. So this is the same thing in momentum space. The first term is the hopping term. Epsilon is the usual tight binding energy. And this is the Hamiltonian. A similar Hamiltonian appearing in this paper here. It leads to a d-wave order parameter. So the superconducting order parameter, again, is the expectation value of this. If we use the equations of motion, we get this. And delta of k can be written as a Fourier transform in this way. And if we use the asymmetry, xy symmetry, we have this d-wave order parameter. So the mean field energy eigenvalues of such Hamiltonian are given by this. This vanishes at the 4 points plus or minus pi over 2a. And if we expand the energy eigenvalues, this energy eigenvalues, around these points, considering a constant energy, we have this expression here, which we can show are ellipses with semi-axis proportional to E. We just plot this, we get this. So you see there are these 4 pockets at those points. And this can be compared with Harper's result. We see it's very similar. So this is the kinematics of our model. Okay, so what we're going to do, we are going to organize the fermion operators in this Nambu, so-called Nambu fermion field. where we have CA, CB up, CA, CB dagger down. Remember, this psi is the whole creation operator in oxygen sublattice A with the spin up or down, and A, here is a label that denotes the layer, copper oxide layer to which the hole belongs, which runs from 1 to n. And then we can write the previous Hamiltonian in this way. So what we're going to do, we're going to impose on this Lambeau fermion field, we're going to impose this constraint that relates the charge. The charge density is constrained to be equal to that expression that we obtained for the net charge per site. So we introduce this as a constraint. Lambda here is a Lagrange multiplier field over which if we integrate over lambda, we get a delta function. So we impose that the net charge associated to the holes are given by this. So we compute the effective action by integrating over the fermion fields. So we get this expression here, where we have here K0, because this must be in order to get the action, we must have the Lagrangian. So we have this is I delta 0 minus H is the Lagrangian. So that's why we have this K0 here. And lambda is the Lagrange multiplier field that enforces the constraint. So the Hamiltonian is the rest. The Hamiltonian is this epsilon, epsilon, and delta part, epsilon. So what we do, we minimize the effective action with respect to the delta and lambda, and thereby we obtain delta 0 and lambda 0, which are the values which minimize this effective action. And then we get this gap equation and the doping equation, minimizing respectively with respect to delta and lambda. Sigma 0 is just the superconducting order parameter is proportional to sigma 0. So in order to find the TC, we put sigma 0 equal to 0. And then we work with these equations. By the way, this is just a remark about, you see there's a lambda here, and there is an alpha. Alpha is the, alpha, okay, you can see here. Alpha is 2 pi VF square. If you square this, cancel 2 pi, you have alpha is 2 pi square. And lambda is an energy cutoff, which is written in terms of the coherence length, which is of the order of 10 angstrom for the high TC cuprates, whereas for conventional superconductors, this coherence length is of the order of 500 angstrom. So if we compute those integrals for delta 0 equal to 0, we get TC, because TC is, in order to get TC, we put the superconducting parameter goes to 0, which means we are on the verge of the superconducting transition. So this is what the gap equation gives, and this was the doping equation. We have these two pieces which are equal. So with a little manipulation of these equations, we get lambda 0, which is the chemical potential, given by this expression, where gamma is this. There is a G, which is the effective coupling of that BCS-like interaction, and GC is given by this. GC is a threshold coupling below which there is no superconducting order. And gamma is this expression here. A is the area associated, the area of the lattice associated to each site, and eta is given by this expression here. So we see here already that the effect of n layers is to redefine the effective G. The whole dependence of n can be put in this form. So n enhances the effective coupling. So the critical temperature we obtain from these two equations is given by this. You see that it is an implicit equation because Tc is here and here, and lambda 0 is the chemical potential given by that. And from here we see that for x equal to x0, remember x0 is the doping for which the oxygen lattice becomes half-filled. For x equal to x0, lambda vanishes. Lambda vanishes, so this hyperbolic cosine is equal to 1, so this log is 0, so this Tc equals T max. So we learn from this analysis that the optimal doping corresponds to a half-filled oxygen lattice. And this T maximal is given by this expression in terms of this eta, where eta is a monotonically increasing function of Gn. So let's apply our results. We start with LSCO, which is given by this gray experimental data. So what we do, we enter with T max and x0, the experimental values, and then we solve this equation and plot it, and we adjust just one parameter, which is lambda, this lambda here, sorry, this gamma. So this is we take this equation, we expand the hyperbolic cosine, and we get this, which is, we use the same equation both in the under and over doped regions. And then we plot this equation. So this is the result we obtain from that solution of that equation by adjusting gamma to this value. And these are the experimental data from these people. So, as I said, the only result we had for this dome was this empiric parabolic fit, which comes from 91, which is this. This is the parabolic fit. And this is a superposition of our result and the parabolic field. Our result is the solid line. So now to mercury and bismuth. Mercury is the green, bismuth the red. As you can see, these domes are asymmetric. The only compound which presents a symmetric dome is LSCO. So now from the original equation, we do two kinds of expansions on the left and on the right. And we get these two implicit equations again. The way we expand is different for the two sides because, for example, this log of 1 plus exponential, you see that in one side we can write this, we can expand in this log 1 plus x, but depending on the side we are, this factor is larger or less, okay, than 1. So that's why we expand differently. So this is for bismuth, the experimental. Again, we just adjust one constant. These are the data. These are the same data in a scale of 300 Kelvin. This is 50 Kelvin. So this for mercury, again, just adjusting one parameter. Again, in a scale of 300 Kelvin. These are the two points where there is a transition at 0 temperature, which we can obtain by just making Tc goes to 0. We get these two results here for bismuth and mercury, and this for lanthanum. So now we have analytic expressions for the superconducting domes, which are have excellent agreement with experimental data. Now for the two other effects which I mentioned. So if you take a multilayered compound, Tmax is given by this. Now if we assume that for one family G and Gc are always the same, we see that the effect of n adjacent planes is to enhance this. So if we take the ratio, we have Tn is just this ratio as T1. So we see we have an excellent agreement. This is theoretical result obtained from this equation, and these are the experimental. So you see for n equals 3, it starts to be a little bit different. So n equals 2, excellent. N equals 3, a little bit different. And for n equals 4 and 5, it's quite different. So we can understand quite easily why this is so, because you see here the charge reservoirs are here, and as we increase the number of planes, there are basically just there is one plane adjacent to the two reservoirs. There is one plane adjacent to each reservoir, but here there is for n equals 3, we start to have a plane that is not adjacent to any charge reservoir. So it becomes, even though we dope the system, the charge goes there, we cannot dope as efficiently the inner planes as we do for the outer planes. So this explains why. So for n equals 4 and 5, we have basically the same result as n equals 2, because only these two planes are being doped. The other ones are not being doped. And therefore, they remain antiferromagnetic. This explains the coexistence. So finally, the two points where the transition occurs at t equal to 0, which we obtain from our general formula by just making t equals to 0. As we see here, x minus, which is this point here, is x0 minus this, and this is a monotonically increasing function. I'm about to finish. So it's very easy to understand why this point moves left, because we can see here this increases, there's a minus sign, so this point moves left. So this is quite easy to understand. So we come to the conclusions. So we have three results: the analytical expression for the superconducting domes, the increase of Tc as a function of n, and the superposition of superconducting and antiferromagnetic domes, for which there was no explanation so far. We have excellent agreement with different compounds. So whatever the theory for high Tc cuprates may be, at a certain point it should explain these issues. So we believe that whatever the theory, whatever the mechanism of pairing is, at some time it must be in the form of the model that we use it here. Optimal doping occurs at half-filling oxygen lattice. And we can devise here even a method for increasing the temperature in cuprates. So it's clear that if you can increase the number of copper oxide planes and at the same time efficiently dope these planes, we would have a real increase in the temperature. So for this we need to intercalate charge reservoirs between every two layers. So this is the hint for the material science people, how to increase the temperature in cuprates. There are many perspectives to be done after this work, like studying the pseudo gap. We are still on this, so soon we'll have some results. Then describing the resistivity in normal phase, pressure effects, and so on. Okay, so this is basically what I have to. Oh, this is just to finish. In a previous papers, we had described the antiferromagnetic dome of LSO. So this is almost complete. So it's still lacking the pseudo gap. Thank you very much for your attention.
Marino, questions, comments,
the quantitative aspect of the result is truly amazing. But I have a couple of questions concerning the superconducting state itself. So before you go to the normal state, you have already a complete theory for superconductivity within this model. So you should be able to check the behavior of, for example, specific heat at low temperature,
Okay.
right? And you should also be able to check the critical behavior around TC,
Okay.
right? Because that's ultimately necessary to show that this particular superconducting state that is basically BCS-like in your model is the same state that the actual experiment have seen, right? Because these are the power law behavior of specific heat at low temperature, or the near TC, the critical behavior. These are very robust features. They are very robust, independent of the detail of the theory.
Okay.
And so if the theory is correct, you should be able to check that they are indeed consistent.
Okay.
And if they are not consistent, then we have a problem, right? That means that the state that we are discussing is probably not the actual state of the real material.
Okay.
So I think that this is something you can check very easily because you already have a almost
Sure.
complete theory.
Sure.
Right?
Okay.
Related to that, you can also check, for example, superfluid density as a function of temperature and doping, right? Those, to some extent, also tells you the detail of this particular state.
Okay.
And as far as I know, the issue like specific heat dimension at low temperature or the critical behavior near TC, both are actually unresolved, meaning that the experiment do not agree with the BCS-like theory.
Okay.
And to me, that's probably one of the essential issues to check.
Okay. Thank you.
Yes. You show a very amazing fitting of the domes for different materials, and with just one parameter, right?
Yeah. We just
what I don't get very well, how this parameter can be connected to the specific structure of each material. Do you have an intuition and waving?
Yeah, because what we adjust is basically the effective coupling of our model, because gamma depends on G. So G let me just show. Okay, you see, G here is if I integrate over phi, I get a quartic interaction with coupling constant G. So when we adjust gamma, we are actually adjusting G, which is the effective superconducting interaction, the magnitude of this effective. So it's presumably it will depend on the compound, on the structure and many things. But of course we don't have a detailed explanation for this because we don't have a theory for high TC superconductivity. But we have an intermediate theory that once we find the basic, so this would be like Landau-Ginzburg theory. So once we find the microscopic theory, we should be able to determine how this G would depend on the details of the compound. Sure.
I had a clarifying question. You say at some point that the optimal doping occurs when the oxygen lattices are not filled.
Yeah.
But later it appears, I mean, that's not true, right? You said X0 is 0.29, which is not exactly half filled.
No. Okay. Let me just. Okay, the way I define this x0 is that when x equals to x0, x is the stoichiometric doping. when x is equal to x0, we have one hole per site, which means have filling of the oxygen lattice. So this 0.29 is the stoichiometric doping. So I call x0 the stoichiometric doping for which the oxygen lattice is half filled, because then I have the number one hole per site. The way I wrote it. The way I write this constraint.
I think I understand the definition, but how do you relate that to, say, the amount of strontium that I add to platinum, strontium, copper oxide, right? That just tells you exactly how much charge I put in. So why does 0.29 strontium give you exactly one?
Yeah, that's a point. We don't have a detailed microscopic model of how the oxygen lattice is doped. But we call x0 the value at a certain stoichiometric doping, it will become half filled. So we call this by definition x0. And we show that for x equal to x0, we have the maximal doping.
I have a question about the orbitals. In the very beginning, you started with a Lib lattice with the px and py, and they were along the bonds of your edge sites. And then when you have put only the oxygen lattice, you have, yes. So you started with px and py,
Yeah.
right?
They are along the links of the copper.
Yes, but now this gray square,
Yeah,
it's
this
what
is
you
the
were
oxygen.
representing later.
Yeah,
And now you have tilted your oxygen.
yeah. Because, as you see, there is... oops.
Yes.
As you see, there is an angle of 45 degrees here,
Uh-huh.
which is this angle here.
Yes, but if you give the freedom, usually, if you have orbitals, and you give them the freedom to rotate, and when you look at your ground state, they should be rotating in a way that the inner lobes all have the same sign, because this maximizes hopping. So I don't understand why you have minus
but
on
this-
the upper lobes and pluses in the lower lobes.
Okay, this is frozen. You cannot rotate them anymore. These p orbitals are fixed.
But those are not along the same direction as the next one.
Yeah, they are, because you see,
No, these are at the kink of the gray.
rotate 45 degrees. This gray square
Uh-huh.
is this square here.
Exactly.
So it's a 45 degrees angle. Yeah.
No, they were perpendicular to what you were drawing. Look at the edge of the gray. They are perpendicular to the edge. And now there they are entering inside.
No,
the
you agree
gray.
that this angle here is 45 degrees.
Yes, but now you are putting them entering inside the gray, and before they were at the corner, perpendicular to what they are there.
No.
No.
Copper is here.
No.
Copper is here.
What I'm saying is that this picture is not the previous picture, because here they are entering inside the gray, and before they were perpendicular to the gray.
No.
No?
The copper is here. Copper is here.
Okay.
Look at this. Look at this.
Yes.
Copper is, the lattice I am representing is this one. So we have copper, one square with a copper, one without. That's exactly here. One copper, one without. One copper, one without.
Okay, but it's okay.
It's
We-
just a
we can
rotation
talk
of
later.
45 degrees.
Okay, I think we have to move on. So let's thank
Thank you.
Eduardo again. Now let's, the other speakers, another Eduardo. 30 minutos.
Tem VGA também, né?
Tem VGA. Tem.
Okay.
Well, next speaker, Eduardo Marino from
Talvez não seja. Ele tá no HDMI ainda, tá? Tem que passar para VGA.
Tá vendo? A academia tá aqui, você tá vendo VGA em algum ponto?